If you've spent any time working with real numbers, you might have noticed a pattern. When you trap a sequence inside a closed interval with clear boundaries, it tends to behave. It doesn't spiral off into infinity, and it usually settles down to a predictable limit. The mathematical property driving this predictable behavior is compactness. It acts as a structural guarantee, ensuring sequences converge, functions remain bounded, and continuity is preserved. It's the tool we use to make infinite sets behave. On page 36 of Rudin, we find the formal framework. Definition 2.31 introduces the open cover, while definition 2.32 establishes what it actually means for a set to be compact. To understand these definitions, picture a closed interval. An open cover is an infinite collection of open sets, translucent circles here, that swallow the target. Compactness guarantees you can discard almost all of them, leaving a finite number of sets that still successfully cover the target. This reduction is significant because it allows us to bridge the gap between properties that hold on small individual neighborhoods and properties that must hold for the set as a whole. A common point of confusion in topology is that openness and closedness usually depend on the parent space a set lives in. A set might be open in one universe, but closed in another. Theorem 2.33 shows that compactness is different. It is an absolute intrinsic property that does not care about the surrounding space. The definition of compactness originates entirely from within the set's own internal structure. If you move a compact set to a new, larger topological space, its internal requirements for finite covers remain exactly the same. Because of this, a compact set brings its reliable properties with it, no matter what topological environment you place it into. This absolute structure forces sets to be well-behaved. Theorem 2.34 proves compact subsets of a metric space must always be closed. Conversely, Theorem 2.35 shows any closed subset contained within a compact set immediately inherits that compactness. Together, these results ensure that a compact set has boundaries that are fully contained and is finite in its total reach. Let's test this intuition. Try to mentally construct an open cover for the open interval from 0 to 1, a cover that cannot be reduced to a finite subcover. The solution is to define a cover using the intervals from 1 over n up to 1. As you stack brackets for 1/2, 1/3, and 1/4, you move closer to 0. But since 0 isn't in the set, any finite number of these brackets will always leave a tiny uncovered gap right at the edge. This proves why compact sets cannot have missing edges. If a point can be infinitely approached but isn't actually part of the set, the requirement for a finite subcover will fail. This strict boundary control dictates how infinite sequences behave. Theorem 2.36 demonstrates that a sequence of shrinking, nested compact sets will always have a non-empty center. Following that, Theorem 2.37 proves that every infinite subset trapped inside a compact set must eventually pile up and have a limit point. A compact set acts like a constrained physical space. Infinite sequences simply run out of room and are forced to converge. In abstract metric spaces, being closed and bounded does not always guarantee compactness. However, Euclidean space, denoted as r to the k, has special geometric properties. This begins with Theorem 2.40, which establishes that every k-cell, like a solid box or rectangle, is compact. This leads to Theorem 2.41, the Heine-Borel theorem. It provides the definitive criterion for analysis in Euclidean space. A set is compact if and only if it is closed and bounded. Because of this theorem, we can identify compactness in standard geometry by checking for clear boundaries and finite limits, rather than wrestling with infinite open covers. To summarize, the definition of compactness requires every open cover to have a finite subcover. This property forces sets to be both closed and bounded, and in Euclidean space, being closed and bounded is equivalent to being compact. Compactness is the mechanism that bridges the properties of individual neighborhoods and the behavior of the entire set, allowing us to treat infinite spaces with finite logic. If this breakdown helped you master these definitions, like and subscribe for more deep dives into the principles of math.